In this video, we're going to do some examples with net ionic equations. So just a quick reminder, we can take a balanced equation and write it in its total ionic form. And in that form, what you do is you take any soluble ionic or strong acid substance and you write it in this dissociated or ionized form, meaning in its form where you separate the ions. Then what you do is you analyze that equation and you see which ions are not really participating in a reaction but are there. And so those are called spectator ions. And if you remove those, you get your net ionic equation. So this is a great video that illustrates that concept of writing net ionic equations. And you'll also see some examples in this video, but this gives you a different perspective if you'd like as well. So let's go to our handout here. So we have total ionic equation, a chemical equation in which soluble ionic and strong acid substances, and then strong acid, SA, strong acid substances, are written in their dissociated or ionized form. And so what that basically means is, let's say you have an ionic compound. If you had, let's say, NaCl AQ, and you want to write it in its dissociated form, you have a sodium ion, so that's Na plus AQ. And then you also have a chloride ion, that's Cl minus AQ, because that's how they're acting or behaving within the dissolved solution. And if you have a strong acid, for example, like let's say HClAQ, you write it as H plus and Cl minus. And so as we saw in the previous video, the rule is that strong acids can be written in their ionized form. So for ionic compounds, we say dissociated, and for acids, we say ionized. Because the reason we say ionized is kind of like the reason behind it is because these are actually molecular compounds. So they're not really ionic, so to speak. There's no metal, non-metal. It's just two non-metals. But when you put them in water, they sort of transform into ions in a way. They behave like ions. That's a simplified way to think about it, but that's why we say ionized. So again, ionic compounds, they dissociate, whereas acids, they will ionize. It's the same result in the end, but just different terminology for it. So we say ionize for strong acids and then dissociate for the ionic compounds. Now, there are some compounds that remain undissociated. The insoluble ones, those precipitates, they stay as a solid. You do not separate them. And also molecular compounds that are liquid or gas, they stay the way they are. They do not separate into ions because they don't exist as ions. So you would not do that. So a net ionic equation is where you take your total ionic equation and you take away all the ions that do not really participate in the reaction. So basically, it does not include what's called the spectator ion. So an ion that is present in a solution but not involved in the reaction is called the spectator ion. And so if you remove those, you get your net ionic equation, which basically means the gist of the story, the most important piece of the story told. And you can also tell what your spectator ion is by looking at your precipitate, which is the insoluble product in a reaction. And typically in the precipitation reaction, it's going to be a solid insoluble product. So let's go ahead and see how all this applies and how we can do some examples of net ionic equations. So these are the main steps: write a balanced equation, write a total ionic equation using the rules of dissociation and ionization, cancel out the spectator ions, and then you have your net ionic equation. If you see that everything cancels out, in other words, everything is a spectator ion, it means no reaction. And you usually see that when you have everything being aqueous on both sides, unless you have the compound breaking down, because the compound that breaks down makes a gas and a liquid. But for the most part, we're going to be focusing on these precipitation reactions where you'll have a precipitate or not. And so we saw in the previous video a little overview of how to do that. Let's go do some examples now. So the next set of pages are basically just examples of writing balanced and total ionic equations and also net ionic equations. So we have silver nitrate and sodium chloride. Those are my reactants. And so I'll put them together. They're solutions because this is solution chemistry. So they're dissolved and all the ions are kind of swimming around in the separate solutions. And then you mix them together and you get these products here. And so that's done for you already. It's just a double displacement and you go take a look at what your states are. And notice that because we have a solid, a precipitate, that there was a reaction. And you need to make sure it's balanced. In this case, it looks balanced. So what we're going to do now is we're going to write a total ionic equation. We're going to separate all the aqueous ones, anything aqueous, into its ions. So we have Ag and NO3. Ag is plus. And it's dissolved in water, so we put aqueous to show that. NO3, that you need to remember from your polyatomic ions, is -1. So I'll put +1, -1 there. And that's aqueous as well. Plus, we have Na, one of them there, and it's Na plus Cl in its ion form, minus Aq. You have to write the Aq. Arrow, we have Na and NO3 again, so we'll put Na plus Aq plus NO3 minus Aq. Plus, be careful here, this is not aqueous, this is insoluble, so the water can't separate it. So we have to leave it as a precipitate together like that. So that one does not change. This is a balanced total ionic equation. As long as you balance your balanced equation to begin with, your total ionic equation should be balanced in the end in terms of charge and amount of ions there, or atoms there as well. So what we're going to do now is we're going to go identify the spectator ions. So for the spectator ions, what we do is we look on both sides of the equation, the reactant side and product side, and see what repeats exactly the same. So notice that here we have Na plus and Na plus on opposite sides. They repeat. And so because they repeat, they are called spectator ions. So Na plus Aq is a spectator ion. And essentially, you could cancel that one out. And you'll also notice that the NO3 repeats on both sides as well. And so you can cut that out because it's a spectator ion. In other words, it's on both sides in the same way, so it's really unchanged. The things that are not on both sides in the same way are your components of your precipitate. So the Ag and the Cl minus, they don't appear on the other side. They're in the precipitate. They're not the exact same way on the other side, so that means that they were involved in the reaction. So everything I circled, those are spectator ions. You can remove them from the equation. And your net ionic equation would simply be the Ag plus 1 Aq plus Cl minus 1 Aq produces AgCl solid. This is your net ionic equation. You'll notice that it's balanced because you have one silver, one chlorine, one chlorine, and the charges are balanced as well. So this is +1, -1, that's 0, and this is 0 on this side over here. So everything is balanced. It doesn't mean the other ions are not there. They are. They're still swimming around the solution, but we just ignore them because they didn't really do anything in the reaction. They just remain swimming around the solution in the same way, the sodium and the nitrate. Whereas the silver and the chlorine, they decided to come together once we poured them together in the same beaker and form this new precipitate over here, which you could filter out if you wanted. So we focused on really what was happening during the reaction. Everything else is still there, but just spectators. So that's why we focus on the net in this case, which is the overall gist of the story. And so that's how you would write a net ionic equation from a balanced equation. If you go sequentially like that, it's pretty straightforward. And this will make stoichiometry, when we get to that later on in solutions, a little bit easier. So let's go try another example. What I recommend you do is you try it out yourself first, and then first pause the video, try it yourself, and then play the video again so you can check your work. So we have aqueous barium chloride reacts with aqueous sodium sulfate. Write a balanced chemical equation, a total ionic equation, and a net ionic equation to indicate the spectator ions. So firstly, I want to identify my reactants. I have barium chloride, so BaCl2, Aq, because it says aqueous, or if it said solution, same idea. And my other reactant is aqueous sodium sulfate, Na2SO4Aq. And so I'm going to write a balanced equation out. So BaCl2Aq plus Na2SO4Aq And I'm going to do a double displacement. So barium will go with sulfate, and that'll be BaSO4 plus NaCl. I have to go check the states because I don't have anything that decomposes, or this is not an acid-base reaction. So I know NaCl is aqueous from previous examples. You can go back and look in your table if you're not sure, but NaCl is just sodium chloride. We have to go look at barium sulfate, though. So let's go up here. Barium sulfate. Let's erase some of this so we can see what's going on. Barium's over here. Sulfate's over here. Barium wants to be insoluble. Barium's higher up than sulfate, so it wins. So that means we have a precipitate. We do have a reaction. All right. So there's a reaction there. And we need to make sure this is all balanced. So we have 2 sodiums on the left side and 2 chlorines. So if we put a 2 here, that should make everything balanced. And I'll put the 1 just to remember I balanced it. So this is a little bit different than the last example because we have coefficients other than only 1 in this case. But every rule is still going to apply. You just have to be careful for when you do have coefficients of more than 1. So let's go ahead and separate or dissociate ionic compounds. So we have 1 barium over here, Ba plus 2Aq. That's the charge from the periodic table. Plus the chlorines, you have 2. Be careful there. If there was a coefficient in the front, like a big number here, like 2, for example, you do 2 times 2, 4. But here it's just 1 times 2. So it's 2 chlorides plus we have 2 sodiums, 2 Na plus Aq, plus sulfate, SO4, 2 minus Aq. Now, notice the precipitate does not dissociate. So BaSO4, solid. Plus, we have 2 sodiums. 2 times 1 is 2, so 2 sodiums. Because that's an aqueous compound. It's dissolved, it's soluble. Plus, and then 2 chlorines. 2Cl minus Aq. So now what we'll do is, that's our total ionic equation. Assuming you balance your equation properly the first time, that should be balanced as well. We're going to go try to identify our spectator ions, and we will cancel them out to make our net ionic equation. So here I have what repeats 2 sodiums, 2 sodiums. So our spectator ions are the sodiums. And it looks like there's also the chlorines that repeat, this and this. So the Cl minus Aq, those also repeat, and they are our spectator ions. It looks like that's about it. And a quick way to really identify your spectator ions is by simply looking at what's in the precipitate. So the barium and sulfate are in the precipitate. They are your ions that are involved, and everything else must be spectator. So we're on the right track here. We can remove the chlorines from both sides and the sodium from both sides. And what we're left with at the end, let's go write that out, is our Ba plus 2Aq plus our sulfate, 2 minus here, or minus 2, Aq. Make sure you put states. And then that produces our BaSO4 solid. So we have 1 barium, 1 barium, 1 sulfate, 1 sulfate. Charges are both the same because 2 minus and 2 plus is 0, and over here 0. And this is our net ionic equation. It's balanced. It shows just what's really happening at the precipitate formation level. The other ions, they're still present in the solution, just still swimming around. They didn't commit to anything new. They didn't change in any way. They didn't form a precipitate. So we just kind of ignore them, especially when we're doing stoichiometry. It makes lives a little bit easier just to focus on what's actually happening in the reaction. Everything else is like background noise. We don't really need to care about it too much. And so that's a net ionic equation for this reaction here. In the next video, we'll attempt a few more problems, but I highly recommend that you try these yourself before going to the next video, and then check the next video to check your answers, to provide yourself with some feedback. The last video is a challenge. The video lesson for it is already here. It's done from a different perspective, but it's a great video. So please make sure that you attempt this one. It is a little bit of a challenge, and I put a little hint to help you with that challenge. So try this once you're done the two previous ones, example A here and B over here. Before you try the challenge, you might also want to reread over, especially the part with ionizing strong acids versus something called weak acids. So just think about that carefully when you try that challenge video there. So next video will be to go over the last examples over here, A and B.